Preliminary design for a residential complex comprising 204 housing units, retail spaces, underground parking, and storage rooms, developed at ARCHITECHTURES. The project site is located in Getafe, municipality in the southern metropolitan area of Madrid. The plot is situated within the urban sector known as Los Molinos, which is regulated by a partial master plan, Plan Partial, as detailed later on. The plot under study has approximate dimensions of 100 meters in length by 60 meters in width, and it is one of the few remaining undeveloped lots in the area. Before generating volumetric options in the design platform, we analyzed the urban layout and building footprints of surrounding developments. This contextual study provides key insights for selecting the most suitable building typologies for this urban context. Upon reviewing the applicable planning regulations from the master plan, we parameterized the main urban planning constraints, including development potential for both residential and commercial uses, primary and compatible land uses, maximum permitted number of flats units, maximum building height, overhangs and projections onto public space, maximum footprint above and below ground, minimum parking provisions, mandatory building setbacks and alignments. Furthermore, we must comply with the client's product mix requirements, which emphasize a majority of 2 and 3 bedroom units, allocating 20% of the development to 1-bedroom apartments. Within the ARCHITECHTURES platform, we proceed to import the site context using OpenStreetMap. By selecting the desired area and clicking the Import button, the model automatically loads surrounding buildings, roads, vegetation, and the existing topography of both the plot and its surroundings. There is an existing protected tree, catalogued by the local Parks and Gardens Department. This element must be preserved and integrated into the site layout. We then enter the main design parameters into the Objectives panel on the left-hand side of the interface. This includes the total of 204 dwellings, the product mix, buildable floor areas, maximum plot coverage, calculation criteria for buildability, e.g., terraces, shared areas, and advanced settings such as surface tolerances and minimum width constraints, which govern the design control parameters. Given that the plot features a slight slope, though with moderate gradients, we define a platform at the elevation allowed by the partial plan. The layout is optimized to accommodate the underground parking structure while minimizing earthworks, thereby reducing construction costs. We proceed with the placement of the first building block, which, following the urban layout analysis conducted earlier, is designed using a through-apartment typology based on a linear block configuration. We also adjust the number of stories and other general floor plan parameters via the input control panel. The first building volume of the development is now in place, as shown in this 3D view of the BIM model, configured with a ground floor plus 5 typical stories, which matches the maximum height permitted by the partial plan. Next, using several tools from the top toolbar, such as reference lines, we model 2 corner buildings with a central corridor layout, aligned to the street grid based on the right-hand axis of the first block. The vertical circulation cores are oriented toward the internal facade. Although these volumes nearly consume the total buildable floor area, we fine-tune the spacing between blocks to improve visual openness for dwellings at the ends of the linear block, and to ensure compliance with the minimum block-to-block distances within the plot, as set out in the master plan. Once the building layout on the plot is finalized, we proceed to refine the product mix, making variations across the 3 blocks to achieve the desired percentage distribution of dwelling types. For greater visual clarity, we can customize the color shading of each unit typology. In this case, 1-bedroom units are highlighted in yellow, while 2-bedroom and 3-bedroom units are shown in blue and red, respectively. By clicking on one of the generated units within the linear block, we can view the proposed internal layout, automatically configured by the tool based on the predefined criteria. This includes secondary bedrooms and kitchen oriented to the rear facade, and the master bedroom and living room positioned on the main facade. Returning to one of the corner buildings with central corridor, we instruct the system to replace ground floor residential units with commercial premises, as stipulated by the urban planning regulations. As shown, the tool subdivides the ground floor into several retail spaces, displaying both net usable area and gross floor area for each. Using the top navigation bar, we access the ground floor of the linear block, and through its corresponding parameters, we define which facades should incorporate private gardens. In this case, gardens can only be placed on the facade facing the inner communal area. We then apply the ground floor commercial allocation to the second L-shaped building, and as seen in the interface, it is also possible to reassign uses of individual spaces to technical rooms, communal areas, atriums, or even create voids where necessary. 1. Remaining within the same building, and in order to further optimize the number of units, we activate the design criteria allowing interior kitchens. This reduces the linear facade length required per unit, thereby enabling the tool to fit an additional unit per floor, as shown. Once satisfied with the automatically generated floor layouts by the AI engine, we can switch to manual editing mode, which allows us to refine any aspect of the design, such as moving partitions, adding or removing doors, eliminating walls to create open-plan kitchens with room dividers, or expanding terrace areas. To complete the above-ground design phase, we proceed to design the communal outdoor areas within the plot. These include swimming pools, landscaped green zones, tree-lined spaces, and sports courts. As a final architectural gesture, we extend the depth of terraces to enhance their spatial quality, particularly in those typologies that allow it, leveraging the remaining buildable floor area surplus. Within the 3D view module, we can generate horizontal, longitudinal, or cross-sections as shown here, in order to verify and control the arrangement of all building levels and validate the implementation. As shown in this cross-sectional view, by elevating the ground floor level through the platform creation, we have minimized excavation depth below grade, thereby reducing construction costs and enabling natural cross-ventilation for the basement level, -1. We then proceed to develop the below-ground structure. The basement perimeter walls can be easily delineated, and the system will generate an initial layout in seconds, with a model that is fully coordinated with above-ground elements such as structure and vertical circulation cores. The user can define a wide range of design criteria, including parking bay dimensions, ramp slopes, structural spans, and perimeter conditions. Using the tools in the top right toolbar, additional drive lanes can be added or modified, with the system adapting dynamically in real time to user inputs. An important design feature in this project is the swimming pool basin, which can be coordinated with the interior basement layout using the trim tool, as demonstrated in the model. To complete the level -1 layout, we add another drive lane and design the external vehicular access ramp. After checking the regulatory parking requirements in the data panel, and seeing we are below the minimum threshold, we proceed to generate a second basement level, along with the corresponding ramp connecting both levels. Once the underground parking layout has been optimized, ensuring the required number of parking spaces and storage rooms, we validate in this 3D BIM section that all floor levels and structural elements are properly coordinated, including the swimming pool basin and the vertical alignment of structural columns across all floors. We now move on to the cost module, where we can monitor the budget in real time. Through the top navigation bar, we can also navigate through the different items of the budget, from the earthworks chapter to kitchen equipment. We can adjust the prices of the various chapters, which can be easily managed using the presets we have previously created in other projects. This example demonstrates how easy it is to modify the unit cost per square meter of slab structures, from €85 to €150 per square meter, with the change being automatically reflected in both the structural cost breakdown and the overall budget estimate. In short, quantities across all work packages are dynamically linked to the BIM model, and the user only needs to manage the unit pricing. At this stage, the entire building design is resolved with a LOD 200 BIM development level, equivalent to a detailed preliminary project, fully aligned with urban planning regulations and the client's initial product strategy, including both above and below grade components. If you'd like to learn more, we invite you to try ARCHITECHTURES.